Hello viewers. In this presentation, we are going to discuss waves. A wave transfers energy from one point to another. There are two types of waves, mechanical waves and electromagnetic waves. The waves which require material medium for their transmission are called mechanical waves or elastic waves. The waves which do not require medium for their transmission are termed electromagnetic waves. Here, we are going to confine our discussion to only mechanical waves. A mechanical wave propagates in form of a disturbance that travels through a medium due to repeated periodic motion of the particles of the medium about their mean position. The motion being transferred from particle to particle without the transfer of the matter. Mechanical waves can be of two types, transverse wave and longitudinal wave. In transverse wave, the particle of the medium vibrate about their mean position at right angles to the direction of propagation of the wave. In a longitudinal wave, the particle of the medium moves back and forth about their mean positions along the direction of propagation of wave. We generally consider a mechanical wave to be of sinusoidal in nature. In order to describe a wave, we usually use the following terms. Amplitude. It is the maximum displacement of the medium from its equilibrium state when a mechanical wave passes through the medium. Wavelength. It is the distance traveled by the wave during the time any particle of the medium completes one vibration or cycle about its mean position. The time period. The time period of a wave is the time taken by the wave source to complete one vibration or one cycle. Frequency. The frequency of a wave is the number of complete cycles that pass a given point in 1 second. Wave velocity. The distance covered by a wave in 1 second is called its wave velocity. Wave velocity, frequency, and wavelength are related to each other as v equal to f lambda. In terms of time period, wave velocity can be written as v equal to lambda by t. Characteristic motion. By wave motion, we mean the transfer of energy from a source to a distant receiver without the transfer of matter between the 2 points. A transverse or longitudinal wave motion has the following characteristics. Wave motion is a disturbance traveling through a medium. When a wave passes through a medium, energy is transferred and the medium particles execute vibrations only about their mean position. That is, there is no net displacement of the particles of the medium. The energy transfer in the medium takes place with a constant speed, which depends on the nature of the medium. The wave velocity is different from the velocity with which the particle of the medium vibrate. The wave velocity is constant throughout the medium, while the velocity of the particles during their vibration is different at different positions. When a wave travels in a medium, the particle which meets it first begin to vibrate a little earlier than the particles immediately after it. In other words, there is a continuous phase difference amongst the successive particles of the medium. A wave motion is possible in a medium which possesses the property of elasticity and inertia. If the disturbance at the source is of repetitive nature, the wave is maintained. If it is not, the amplitude of vibration of each particle becomes progressively smaller and eventually the wave ceases to exist. If the disturbance at the source is simple harmonic, a plot of displacement of the particle at a single instant in time as a distance from the source is sinusoidal. Speed of transverse and longitudinal waves in different medium is given as velocity of transverse wave in solid v equal to eta by rho. Velocity of longitudinal wave in solid v equal to square root of k plus 4 by 3 eta by rho. Velocity of longitudinal wave in rods v equal to square root of y by rho. Velocity of longitudinal wave in liquid and gas v equal to square root of k by rho. Sound waves are longitudinal waves and can travel through any medium. Now we are going to discuss the velocity of sound in gas. Newton assumed that the sound waves travel through a gas under isothermal conditions, and the appropriate modulus of elasticity will be isothermal Bach modulus. Accordingly, speed of sound in gas is evaluated as v equal to square root of p by rho, which comes out 280 meter per second, which is quite less than the experimentally observed value. Laplace made a correction into this process. He said, due to rapid occurrence of compression and rarefaction, heat exchange could not take place with surrounding. Hence, the appropriate modulus of elasticity should be adiabatic bulk modulus. After implementing Laplace's correction, the velocity of sound we get approximately 331 meter per second. This is in close agreement to the experimentally obtained value. Velocity of sound in a gas is affected by various factors such as density, molecular weight, temperature, humidity, etc. Speed of sound is inversely proportional to the square root of the density. Speed of sound is inversely proportional to the square root of the molecular weight. Velocity of sound is directly proportional to the temperature of the system in absolute scale. Velocity of sound is independent of pressure. Though velocity of sound wave is independent of frequency, but humidity and wind speed can alter the velocity of sound wave. The function involving position and time, which describes mathematically the motion of a wave pulse, are called wave function. The general form of the wave function is y is a function of x plus minus vt. The wave function represents y coordinate of any point at any time. In case of simple harmonic wave traveling along the positive direction of x-axis, the wave function y equal to a sine 2 pi by lambda vt minus x. When two progressive waves of the same wavelength and amplitude travel with the same speed along the same straight line in the opposite direction, these waves interfere to produce stationary waves or standing waves. The following illustration shows the formation of a stationary wave. The expression representing the stationary waves is y equal to 2a cos kx sin omega t. The periodic variation in intensity at a given point due to the superposition of two sound waves of slightly different frequencies traveling in the same directions are called beats. The frequency of beat is the number of intense sound heard per second. The equation for beat frequency, resultant wave frequency, and wave amplitude is also provided.